Hello, curious minds. Did you know sound is a bit like your mom's impatient tap on the table? It really depends on how quickly things around it bounce back. Today, we are diving into how sound speed changes depending on the medium it travels through, especially focusing on gases. First off, the speed of sound in a gas isn't random. It depends on two big players, elasticity and density. Elasticity is like the gas's springiness, how fast it can snap back to its original state after being squeezed. Think of it like a trampoline, the stretchier and quicker it rebounds, the faster the bounce. In gases, this bounce back ability is measured by something fancy called the bulk modulus, symbolized by B. Meanwhile, density, denoted by the Greek letter rho, tells us how heavy or packed the gas particles are. Putting it all together, the speed of sound, which we call v, equals the square root, that's the number which, when multiplied by itself, gives a value of the bulk modulus divided by density. So, in words, v is equal to the square root of v divided by rho. This means if the gas is more elastic, higher B, sound travels faster, but if the gas is denser, higher rho, sound slows down. Hey again! Ever noticed how on hot days your voice seems to travel a bit differently? That's because temperature has a starring role in how fast sound moves through gases. Sound speed increases as the temperature rises, and here's why: when molecules heat up, they start to dance faster. These energetic molecules pass along sound waves more quickly, like a game of fast tag. For an ideal gas, the speed of sound V equals the square root of the adiabatic index gamma multiplied by the gas constant R multiplied by the absolute temperature T, all divided by the molar mass m. Say that again. Speed V is the square root of gamma times R times T divided by m. Here, gamma is a number that tells us how the gas behaves when compressed or expanded. R is the universal gas constant. T is temperature measured in Kelvin, that's degrees Celsius plus 273, and m is the gas's molar mass. Since V is proportional to the square root of temperature, if you double the absolute temperature, sound moves roughly 1.5 times faster. For example, in dry air at 0 degrees Celsius, sound travels about 331 meters per second. If the temperature climbs by 1 degree Celsius, the speed picks up by roughly 0.6 meters per second. Picture a line graph with temperature on the bottom, from cold to hot, and sound speed rising smoothly from that 331 mark upward, curving gently upward like a friendly hill. This explains why your voice travels better when you're cozy and warm, but gets a bit sluggish on chilly mornings. So next time you're sweating in the sun, just remember, those faster molecules are helping your sound get to your friends quicker. Let's talk gas. Did you ever try to sing after inhaling helium from a balloon? Your voice goes all funny and high-pitched. That's because sound travels faster in lighter gases. Here's the scoop: the speed of sound depends inversely on the square root of the molar mass m of the gas, that's the average mass of 1 mole of its molecules. Lighter gases have smaller molar mass, so sound zips through them faster. In fact, V is proportional to 1 divided by the square root of m. Take hydrogen gas, H2, with a molar mass around 2 grams per mole, versus oxygen gas, O2, which clocks in at about 32 grams per mole. Since 2 is much smaller than 32, sound travels way faster in hydrogen than oxygen, kind of like racing a lightweight sports car versus a heavy truck. Imagine a scatter plot, with molar mass on the bottom going from light gases like helium and hydrogen to heavier ones like oxygen and carbon dioxide, and speed of sound on the side shooting downwards as molar mass increases. Lighter gases shoot sound speed way up. This principle explains why when you breathe helium, your voice sounds like a chipmunk's, faster sound speed raises the pitch. So molecular weight is a big deal. Lighter molecules mean faster sound and a more helium U. Just don't breathe too much helium though. Singing like a cartoon chipmunk is fun, but air is still better for your lungs. The mystery of humidity. Ever noticed how sound might carry differently on a dry day versus a muggy one? That's because the water vapor floating in humid air changes the game. Humid air contains water vapor, which is lighter than the usual nitrogen and oxygen molecules crowding around us. Since water vapor has a smaller molar mass, it lowers the average molar mass m of the air mixture. Remember, speed of sound V equals the square root of gamma times r times t over m. So, as m goes down, V goes up. This means that in humid air, sound travels faster, by up to about 1% faster compared to dry air at the same temperature. How much is 1%? Well, it's enough that outdoors, humidity can subtly tweak how we hear sounds and even make a difference for things like weather monitoring and outdoor acoustics. Picture a bar chart with two bars side by side, one for dry air and one for humid air. The humid air bar is just a little bit taller, showing a small but noticeable speed boost. So, the next time you're by the seashore or in a tropical jungle, remember the moist air is giving sound wings. Humidity is nature's secret speed booster for sound. Pretty cool, right? Time for some number crunching. Let's see how this works in real life using the formula for sound speed in gases. Suppose we are given air at 27 degrees Celsius and we know gamma, that's the adiabatic index, equals 1.4 for air. The gas constant R is 8.314 joules per mole Kelvin and the molar mass m is about 29 grams per mole. We need to first convert that molar mass to kilograms per mole. 29 grams equals 0.029 kilograms. Next, we convert temperature to Kelvin by adding 273, so 27 plus 273 equals 300 Kelvin. Now let's plug these into the formula. V equals the square root of gamma times r times t divided by m. So, V equals the square root of open bracket 1.4 times 8.314 times 300 close bracket divided by 0.029. Calculating that gives us approximately 347 meters per second. That means in air at 27 degrees Celsius, sound travels about 347 meters every second, which matches well with what experiments show. This example isn't just math, it shows us how physics formulas help predict real-world things, like how your voice travels across a classroom on a warm day. Numbers don't lie. Alright, let's sum it all up like a physics rap, but with words. The speed of sound in a gas depends heavily on how elastic the gas is and how dense it is. We say V equals the square root of bulk modulus over density. More elasticity means faster sound, more density means slower sound. In ideal gases, we refine this to V equals the square root of gamma times r times t over m, highlighting that speed goes up with temperature, the hotter, the faster. Plus, sound speed is inversely proportional to the square root of molecular weight, so lighter gases like helium let sound race through quicker. Don't forget humidity. Adding water vapor lowers average molar mass, giving sound a nice speed boost in moist air. So, whether it's the type of gas, the temperature outside, or how muggy the air feels, all these factors play together like an orchestra, making sound move just right. Understanding these gives us the power to predict sound behavior accurately. That wraps up today's lesson. Remember, physics is way more fun when you laugh and learn along the way. Catch you in the next session. Keep those molecules moving.